Hello, my name is Mira Welner, and I'm a student at the University of California, Davis. Today, I'm going to be talking about my research on hyperspectral images conducted at Carnegie Mellon University with Professor Aswin Sankaranarayanan. Hyperspectral images can be used to determine which materials are found in a substance. This is useful in many fields, including climate science and microbiology. The materials within hyperspectral images are typically determined by matching spectra to materials with similar spectra. This requires some degree of knowledge about which materials are expected to be found. My research eliminates this requirement by using unsupervised learning to identify the three most prominent spectra within an image. When tested on the Harvard Real-World Hyperspectral Images database, this model yields a mean squared error validation loss of 0.013. These very promising preliminary results indicate that unsupervised learning can be a useful way to study hyperspectral images. First, I'm going to describe what hyperspectral images are. So, most humans see the world in three colors. Low-frequency light appears red, medium frequency light appears green, and high frequency light appears blue. Computers replicate this by displaying images using a matrix to represent each of these three bands. Each value in the matrix represents a pixel in the image. If a pixel has prominent red coloring, its corresponding value will be very high in the red matrix and lower for the blue and the green. Hyperspectral images are obtained using special photography equipment, and they divide the spectrum into many more bands which are stored on the computer as sets of mini matrices, one matrix for each band. In order to study the three primary spectra of the image, I developed a modified autoencoder. A standard autoencoder uses convolutional neural networks to encode an image into a compressed version of itself, and then again uses convolutional neural networks to decode it back into its original state. In this autoencoder, however, the decoder uses matrix manipulation based on the inherent properties of hyperspectral images. It assumes that the encoded image represents the three spectra, and then uses that assumption to decode the image. The encoder is trained to compress the images in such a way that the decoder works well. This results in a compressed data describing the three primary spectra of the image. This is based on the assumption that a hyperspectral image can be approximated by the sum of three spectra, each multiplied by their respective material map, a material map, in this case, being defined as a matrix representing the distribution of the spectra across the image. This assumption is based on the observation that many scenes can be approximated by assuming that they consist of only three materials and two light sources. While this preliminary study is very promising, further research must be conducted on the efficacy of this model. Following steps that must be taken include applying this model to alternate datasets, including datasets with different scenes and datasets with different number of bands, to ensure that a multitude of datasets yield models with high accuracy. In addition, this model seems good at predicting the primary spectra, but it has a weaker accuracy in predicting material mass, which is a problem that must be addressed. And finally, it must be determined that the spectra produced are actually similar to spectra likely to be found in the image. For example, if a scene contains carbon, one of the spectra should be somewhat similar to the carbon spectra. Hopefully, these next steps will result in the development of a model that can reliably be used to predict the three primary spectra of any hyperspectral scene with a high degree of accuracy. Thank you.